I want to finish up the discussion of planetary motion. So we've proved all the things I wanted, but there's just a few odds and ends that I thought I'd mention at the end. So let's have a quick summary of what we've done. We started off by talking about Kepler's second law. So that was the law about equal areas being swept out in equal time. And let me see, we showed that was equivalent to the quantity r squared theta dot being conserved over all time. And that was equivalent to the only acceleration of the planet being in the radial direction towards the sun. So that was equivalent to motion under a central force. So we were in that usual setup. We had our planet orbiting around the sun, and remember our initial conditions. We assumed that it was moving at velocity v0, a distance r0 away from the sun. So its initial motion was at right angles to the x-axis there, and then there was the planet. Maybe it was Earth. There it was what it was, wasn't it? And so the force was just directed towards the sun. And so Kepler's second law, you didn't need to know anything other than that the force was a central force. To get Kepler's first law, we needed to know more about that force. So this is where Newton's inverse square law came in. So if we assume that the central force is given by Newton's law of gravity, so little m is the mass of the Earth, and big M is the mass of the sun, so if the force is given by Newton's law of gravity for some constant g, we showed from that the equation, the polar equation for the orbit of the planet was the polar equation for conic section. So here E was, we got E as being v0 over v crit squared minus 1. That's the way I wrote it, where v crit, this thing I called the critical velocity, was the square root of gm over r0. And I mentioned but didn't prove that actually that was an if and only if. If you assume that the r satisfies that equation, it's not really a big deal to prove that the central force has to satisfy the inverse square law. So Kepler's, and of course that equation being the equation of an ellipse, that's Kepler's first law. Orbits are ellipses. So providing the number e, that's the eccentricity, is less than 1, you get an orbit that's an ellipse. But as soon as e is greater than or equal to 1, so that turned out to be when v0 was, so e equals 1 is the case where v0 is root 2 v crit. So this is what's called the escape velocity. If the initial speed of the planet is that or bigger, then the orbit's either a hyperbola or a parabola, but either way the planet escapes the sun's gravity altogether and goes to infinity. So I gave you another way of seeing that important velocity, root 2 v crit. There's a way to work out what that critical velocity is, just using conservation of energy without solving all those differential equations. You just have to give the planet at time 0 enough kinetic energy to give it to be equal to the potential energy that you need in order to move the planet to infinity. And you can do that calculation quite directly. So that was Kepler's first law. And then we also proved Kepler's third law. So this is to do with the period, capital T, of the orbit. And we showed that T satisfied the formula 2 pi a to the 3 over 2 over root GM, where A here was the major radius of the ellipse. And from that we were able to, that stronger result easily implies Kepler's third law. So that's where we've got to. We proved all of Kepler's laws, and you see how the calculus in place is just perfect for doing this. This was indeed the problem that must have motivated Newton at the time. So here's a fun little application of that third formula. So for all the planets in our solar system, the eccentricity E turns out to be rather close to 0. I looked up what it is for the Earth on Wikipedia. So for the Earth, so E, let's maybe put a little subscript, E Earth, the eccentricity of the Earth's orbit is 0.016. So the orbit is close to being circular. If remember, eccentricity 0 is a circle. It's not exactly a circle, and that has some implications for life on Earth. I live in the northern hemisphere, and I think summertime for me is a couple of days longer than wintertime, and the reason for that is this slightly eccentric orbit. Okay, but so now if you want to find highly elliptical orbits in our solar system, you can't look at the planets, you have to look at other orbiting objects. In particular, there are comets, and the most famous comet is Halley's Comet. And this has eccentricity that's really close to 1, 0.97. So if you were thinking about, so here's the Sun, this would be Earth in its pretty circular orbit. Halley's Comet's going to be in this highly elliptical orbit around the Sun, something like that. So let me see, it's known that the major radius A for Halley's Comet is roughly 36 times the major radius for Earth, right? So for Earth, that major radius is basically a circle. The Sun is basically the focus. That's the A Earth. As for Halley, you would have to find the midpoint of that elliptical orbit, and then it would be that distance there. Okay. So let's see if we can calculate the period for Halley's Comet. So by our formula, that's 2 pi major radius to the power of 3 over 2 divided by root GM. And if I replace A Halley by 36 A Earth, by that little factor that I fed you, I can rewrite this. If I pull out that 36 out the front, that's a 36 to the 3 over 2 out the front, then I'm left with 2 pi A Earth to the 3 over 2 over root GM, because this is the period of Earth's orbit by our formula, which is, of course, 1 year. So the period for Halley, then, it's 36 to the power 3 over 2 years, which is roughly 76 years. So Halley was a contemporary of Newton, and Newton would have shown him his results about planetary motion. And in the year 1682, Halley's Comet passed close to the Earth, so it was observed. And Halley's contribution was to kind of fit together some of the historical record. There were comet sightings in 1607 and 1531. It would have been quite hard to track down that information and make that realization. But Halley came up with the theory that In fact, these 3 comet sightings were actually the same comet. And you see, there we are. The period is roughly 76 years. So that was quite convincing that indeed this was the same comet, and Newton's formula for period of orbit was just right. There's so much to say here. It's kind of a fun historical subject. You can go and look up stuff on Wikipedia. Look up Halley's Comet or something, and there's tons of interesting things there. It's worth saying that the period of Halley's Comet is not exactly 76 years. In fact, it changes over time. I think it's quite a bit less now, like 72 years or something like that. So what's going wrong here? In proving these laws, what we've always assumed is that there's just the sun and the planet in orbit around the sun. But of course, there's lots of other planets in orbit, and they all have a gravitational pull on all the other ones. It doesn't make such a big difference for planets. They're rather large, but for some little thing like a comet, the effect of the other planet's gravitational pull on that comet has a significant effect. We were just assuming we had the two-body system in solving these differential equations. In fact, for something like Halley's Comet, you've got to take into account the gravitational pull of all the other planets. So you have this incredibly complex, many-bodied system, and you can't exactly solve these equations anymore. But this is the reason that Halley's period is changing over time. You've got to take into account the gravitational pull of all the other planets too, which is mathematically much more difficult. Okay, so that's planetary motion. I think it's a nice classical topic, and it's rather beautiful. Let's move on. I'm going to kind of do some kind of odds and ends for a little bit. So one thing that we used last time in proving Kepler's third law, I needed to know the formula for the area of an ellipse, and that was pi AB. That was for the ellipse given in this standard Cartesian form that we've seen. So that's quite easy to prove that formula. You just have to, I just think of it as stretching a circle. So it's just the formula pi r squared, where you've scaled in different scale factors in the x and the y directions. So you don't even need to calculate that area of ellipse. You just kind of know it for that reason. But we've been working with the ellipse in polar coordinates. Right, so we've had this form recently, and so what I had to do when proving Kepler's third law was translate the pi AB formula into a formula in polar coordinates. So we needed to know a little bit of stuff. We needed to know that the eccentricity was 1 minus b squared over a squared. And from that we got that b was a root 1 minus e squared. And so then so from there I got that actually the area was pi a squared root 1 minus e squared. So that's a little bit closer to the polar equation, but we should still replace the number a by r0, because we don't have an a in our polar equation. And so r0, that was the distance. So that was in the graph, that was what I called a minus c, where c was the x-coordinate of the focus, and c was ae. So in fact, r0 is a 1 minus e. So if I use that and replace a, then a gets replaced by r0. So a squared is r0 squared over 1 minus e squared. And then I've got that root 1 minus e squared still on the top. But 1 minus e squared is 1 minus e, 1 plus e, and it's all to the power of half. And if I do a little bit of cancelling, then I get the final formula that I want. So it's pi r0 squared 1 plus e to the power of half divided by 1 minus e to the power 3 over 2. And so that's the formula for the area of an ellipse when you're given it in polar coordinates. You're given R0 and E. It's rather gruesome, right, with all these nasty halves and 3/2s. And so it kind of occurred to me as I was writing that formula down, how would you prove that directly? So that formula there, can we prove it directly? I mean, we know how to calculate area under a sector in a polar graph. It's integral. It's a half r squared d theta as you integrate between your two angles, theta1 and theta2. So if I were to use that and the polar equation for the ellipse, what would we get? Let me see if I can do it. So I'm using that polar equation. How about I just go from angles 0 to pi? So that would be actually just half of the ellipse. So then I can ignore the half out the front because I've got to double that area. And then r squared is, let's see, r0 squared is a constant, 1 plus e squared is a constant. So I could bring them out the front. And then I've got this 1 plus e cos theta squared d theta. So this we kind of expect, because we secretly know the answer from this Cartesian approach, this had better equal this number. So we'd better have that integral from 0 to pi d theta over 1 plus e cos theta squared, it had better be equal to this stuff. I've got to divide by r0 squared, and I've got to divide by 1 plus e squared. And so when you do that, this is what we're expecting. It's going to be 1 minus e squared to the 3/2. I did a little simplifying. How to show this? That guy there is a pretty nasty integral. So I've sort of justified that we're expecting that this definite integral is equal to this number. But that's kind of by this roundabout way of translating from polar to Cartesian coordinates, moving the origin, and then calculating the original area of the ellipse in Cartesian coordinates. But can we directly show that this definite integral is equal to this number, which would give a direct way of getting this area formula? So this is kind of a good point to maybe stop the recording and go and have a go. See if you can find a way of calculating that integral. It's quite a difficult one. But there's probably several approaches. I'm going to show you one in a second, which is quite complicated. But maybe there's an easier approach which you can discover for yourselves. So I'm going to tackle that integral using a famous substitution. So this is really what I wanted to talk about at this point. So the substitution is t equals tan theta over 2. This substitution is really excellent for integrals involving some angle theta and trig functions, sine theta, cos theta, tan theta. And that's kind of what I've got here, right? I've got an integral. There's an angle theta, and look, it involves cos theta in it. So this is a sort of situation where you can always try this substitution. So let's see if we can work out a few things. So I'm telling you that you can get cos theta, sine theta, and tan theta quite easily in terms of the new variable t when you make this substitution. And I guess I should rewrite that a little bit. If I take this equation and I take arctans then that's theta over 2. So if I double, that's theta, right? So that's another way of thinking about the substitution. Theta is twice arctan t. And if I differentiate that equation with respect to t, the derivative of arctan t is 1 over 1 plus t squared. So I get that 2 over 1 plus t squared is d theta by dt. So that's how the substitution is going to go. D theta is going to be replaced by 2 over 1 plus t squared dt. And we've got to work out cos theta, sine theta, and tan theta in terms of t. Let me quickly do that. Cos theta is double angle formula, 2 cos squared theta over 2 minus 1. I want to turn that into tan, right? So cos squared is 1 over sec squared. And so that's 2 over 1 plus sec squared is 1 plus tan squared. So what have I got? I've got 2 over 1 plus t squared minus 1. And if I put that all over that common denominator, 1 plus t squared, then I get what? 2 minus 1 minus t squared. Okay, so that's how we're going to replace cosine. And let me fill that in up top. So cosine, here's the master formula we just derived, 1 minus t squared over 1 plus t squared. The other one that's pretty easy is tan. Because we know the double angle formula for tangent. We've used that before. Tan theta is 2 tan theta over 2 over 1 minus tan squared theta over 2. So that's what? 2t over 1 minus t squared. So tangent's easy. It's 2t over 1 minus t squared. And then sine, well, sine is cosine times tangent. So if I multiply my two formulas together, the 1 minus t squareds cancel, and you get the formula for sine, 2t over 1 plus t squared. So what will happen when you make this substitution, you'll be able to replace all the trig functions by these rational expressions. Rational function means polynomial over polynomial. And d theta, you'll get another rational function. So when you make this substitution for some integral involving angle theta and trig functions, you'll always get a rational function of the variable t. And then you can always integrate any rational function. There are good methods to do that. You factorize the denominator and you use the method of partial fractions. So this substitution is quite useful for these sorts of trig integrals. So let's just do a little warm-up and see if we can calculate something fairly easy. Let's see if we can calculate the integral of secant theta d theta. Perhaps you already know that one because it's a standard one. It's usually written on formula sheets, but it's a hard one to guess if you don't know the answer. But you can discover it using this substitution. So let's do that. So secant is 1 over cosine. And so I can make my substitution. And I'll get rid of that cosine. The d theta will become 2 over 1 plus t squared dt. 1 over cosine, well, that's cosine. So 1 over cosine is the reciprocal of that. 1 plus t squared over 1 minus t squared. And then those cancel. And so I'm left with 2 over 1 minus t squared, but that's 1 plus t 1 minus t by difference of two squares. And that I can write in partial fractions. But I can factorize that denominator, so I should be able to write it as something over 1 plus t and something over 1 minus t. And in this case, it's rather easy. You don't have to think very long to work out what the somethings are, what the constants up at the top are. It's just 1 and 1 does the trick. So you can easily check that. I'm not going through partial fractions here. I'm assuming you know how to do that. So now we can integrate, right? It's ln 1 plus t minus ln 1 minus t. Or a bit better, it's ln 1 plus t over 1 minus t. So we've calculated the integral, except we've got the answer in terms of t, and we want to go back to theta. So you have to do a little bit more algebra here. What you should do is you should times top and bottom by 1 plus t. So on the bottom I've got 1 minus t times 1 plus t, which is 1 minus t squared. And so what have I got? I've got, let's FOIL out the top. So that's 1 plus t squared plus 2t, and then it's over 1 minus t squared. So I've separated into two fractions. And now I'm very close. This guy here, that's 1 over cosine. So that's secant theta. And this guy here, that's tangent. And so that's the final derivative. The final integral of secant is ln secant plus tangent. And once you see that, it's dead easy to take that and differentiate back again. Derivative of ln is 1 over, so you get 1 over secant theta plus tangent theta. But then you have to times by the derivative of the inside. Derivative of secant is secant tangent. Derivative of tangent is secant squared. And you write it all out and you see the denominator cancels into the numerator. And you're left just with secant theta. Okay, but as I said, you probably saw that integral and knew the answer was ln secant plus tangent. But there it is. There's one way of deriving it. You know, it's often the case with this substitution. This substitution is often kind of a little bit overkill to do it this way. And you could probably calculate that integral in some other way if you wanted. You know, you might write it as 1 over cos theta. You might come up with the idea of timesing top and bottom by cos. And then rewriting the denominator as 1 minus sine squared. And then you can do partial fractions because you can factorize that denominator and then write it into two fractions. And without having to do any substitution, you'll end up with this ln secant plus tangent kind of more directly that way. So it's not really necessary to use this crazy substitution, but it was just a warm-up example. So this substitution is a bit of a hard one to kind of get used to. I mean, it seems crazy the first time you see this at this point. I've just handed it to you, but it actually comes from somewhere. So it actually comes very nicely from geometry. So let me explain that to you a little bit. So I'm going to want to have a unit circle. So there we are, unit circle. And I'm going to think about some point on the circle. So we're used to parameterizing the circle by the angle theta. So that would be our theta. And so the picture we're going to need is this one. So I think I need to go and do a little bit of warm-up work. So let's go and do a little bit of prep work for this. I need to make sure that we know some of the geometry of circles. So this is classical Euclidean stuff. So let's quickly kind of review the classical Euclidean stuff. So there's a circle, and what we're interested in is if you have a chord. So that's a chord. So that's just 2 points joined up on the circumference of the circle. And let's join that chord to the middle and to some point on the circumference. So there's a triangle to the center, and here I'm going. Let me see. It's going to be a bit. Let me try and make it look a little bit nicer. So let's see if I can get this better. I should have drawn a longer chord, then my picture would look better. So this is just some point anywhere on the circumference. And so let's see, that's the picture I wanted. Let's put in one more edge here. And let's think about some angles. So what's this angle here? Let's call that angle alpha. It's the same as that angle there, alpha, because that's a radius and that's a radius. So this is an isosceles triangle. And if those are both alpha, well then in this triangle, that angle there must be pi minus 2 alpha. Great. And let's call that angle there beta. Likewise, that's beta because we've got an isosceles triangle. And so that angle must be pi minus 2 beta. And in that case, then this angle right here, because this is a circle, so these have all got to add up to 2 pi, this must be what's left, 2 alpha plus 2 beta. So 2 alpha plus beta. So what have I just shown? I've just shown that if you have this situation, you have a chord, that angle at the center and that angle on the circumference, well, one is double the other because this angle is alpha plus beta and that angle at the center is double 2 alpha plus beta. Okay, so this is this kind of simple fact that hopefully you have seen somewhere about circles. If you have a chord and you go to any point on the circumference, that angle, no matter where your point on the circumference is, you always get that same angle all the way around, right? So any angle on the circumference coming from the same chord is the same. Okay, so let's go back here, and you see this is what I need here, because here's my chord. There's the angle at the center, and there is the angle on the circumference. So this geometry of circles tells us that that angle there is theta over 2. Now I'm going to let t be that coordinate, where that straight line joining our point on the circle to this special point at -1, 0. I'm going to let t be the y coordinate, where that line crosses the y-axis. So can we calculate t? Yes, we can, because we've got a right-angled triangle here. We know the angle. T is the opposite side, and the adjacent side is 1. So t is tan theta over 2. So this is the t in our substitution. And what's going on here is that you're used to using theta to parameterize this point on the circle, the angle theta there. But you can also parameterize this point on the circle in this kind of slightly weird way. You join that point to -1, 0, and you look at that value t, where that line crosses the y-axis, and you use that number t to parameterize the point on the circle. So let me see, we just showed that cos theta is 1 minus t squared over 1 plus t squared, and sine theta is 2t over 1 plus t squared. We just used the double angle formula to do that on the previous slide. So instead of the moving point being cos theta sine theta, we can write it as 1 minus t squared over 1 plus t squared, 2t over 1 plus t squared. And instead of having it being parameterized by theta, this angle that's moving around, it's now parameterized by this number t, which is this number moving up the y-axis. Right, so it's like here, that would be t equals 0. That point on the circle, there's the t. It's a point like here. What t would it be? T up here, and so on. So and to get the bottom half of the circle, you'd need t's down to that point would be this negative value of t. And you see that the number t parameterizes the unit circle, except for the point -1, 0. This special point you don't get this way, because that would sort of be, you'd kind of need t equals infinity, which doesn't make sense to get to that special point. But all the other points on the unit circle, except that one, get parameterized by this formula, by that y-axis intercept t. So hopefully that makes this substitution kind of have a little bit more reality to it. It's really very natural from this picture. In fact, this picture, you can do all sorts of cool things with this picture. I'm not going to go into the detail, but for example, you might be able to calculate this length. The length, so let's see, we've got another right angle triangle here. And you can calculate the length of the hypotenuse of that right angle triangle. You can calculate it because you know the height is sine theta and the width is 1 plus cos theta. So you can calculate this hypotenuse length using Pythagoras. But another way of calculating it would be to split that triangle in half. That's an isosceles triangle. Just drop the perpendicular, and then you can calculate that length using that right angle triangle, because you know the angle and you know the hypotenuse is 1. So that length would be what? Cos theta over 2, and then another one. So you could calculate that length is going to be 2 cos theta over 2. So you calculate this length in two different ways. And what you end up with, because they must be equal, you end up by proving the double angle formula. For cosine. So I'm not going to write any of that down, but we've used that double angle formula many times. This is a very nice, clean geometric proof of the double angle formula by computing the length of that hypotenuse in two different ways. That double angle formula is what we needed. Remember when I derived those two formulas down below. So somehow this is really where it should all begin, with this picture. But there we go. Okay, so there's the substitution. Maybe that picture makes it look a little bit less of a crazy one, and it actually has a rather natural geometric origin. And I'm going to come back to this picture tomorrow and do a little bit more with this geometry, because it's rather a fun classical story here. But let's see if we can, as the last thing today, let's see if we can actually use this substitution to calculate the integral as I promised. So that was the integral we were trying to do, and so we're going to try and do it using my crazy substitution, t equals tan theta over 2. So remember, d theta is 2 over 1 plus t squared dt, and cos theta is 1 minus t squared over 1 plus t squared. So let's just apply those instructions. So the d theta is 2 over 1 plus t squared dt, and then I've got this 1 plus e cos theta is 1 minus t squared over 1 plus t squared. Okay, so that's done the substitution. Oh, I've got to change the limits as well. This is when theta's 0, so t is 0. And this is when theta's pi, tan pi by 2, well, that'll be, so t will be going from 0 to infinity here. That's not too bad. So let's see, I don't like fractions inside fractions, so let me sneak in an extra 1 plus t squared and another one there. And then this is going to equal, so bring the 2 out the front, integral from 0 to infinity. So I've got 1 plus t squared on the numerator. And I'm doing this because then I can bring those 1 plus t squareds inside there, and get rid of that fraction within the fraction. Okay, so that's our integral, which I can rewrite again. Sorry, this is going to take me a little while. This is quite a calculation. So what have I got? I've got 1 plus e plus 1 minus e t squared dt, all squared. So that's all squared. There we go. So now I don't know if this is a... Maybe I do one more rewriting. Maybe I'll bring out 1 plus e squared out the front. So I've got 1 plus t squared. Then inside there, instead, I'm going to have 1 plus 1 minus e over 1 plus e t squared dt. When you have... So this is, as I promised, this is a rational function of t, and the denominator is factored into this quadratic factor, 1 plus this nasty constant t squared, all squared. So when you do that, then we're not going to do any partial fractions here because there's only one type of factor, but we now need to do another substitution. So now we need to let 1 minus e over 1 plus e t squared, we're going to let that be tan squared. I need some other angle, phi. Or better, square root 1 minus e over 1 plus e t is tan phi. So I'm going to do this substitution to turn that into a tan squared, and then I'll have 1 plus tan squared, which is sec squared, and it'll get rid of that nasty factor on the denominator for me. So here's the substitution I'm doing. Let me see. So dt is going to be root 1 plus e over 1 minus e sec squared phi d phi. So here I'm going to do it. So I've got the 2 over 1 plus e squared already. I'm going to need an extra 1 plus e over 1 minus e. And then I'm going to have the 1 plus t squared. The dt is going to give me a sec squared phi d phi. And the point is that on the denominator, I'm going to have 1 plus tan squared phi squared. I've still got the numerator, right? 1 plus t squared, which is what? 1 plus e over 1 minus e tan squared phi. It might not look any better to you, but we're actually very close because this is sec squared phi. And so some sec squareds cancel. And let me write one more time. Let me pull that 1 minus e out the front as well. So I'm going to have 2 over, how many 1 plus e? I've got 1 plus e squared there, but 1 plus e to the half there. So I've got 1 plus e to the 3 over 2. I'm pulling out another 1 minus e, and I've already got a 1 minus e to the half. So I'm going to have a 1 minus e to the 3 over 2. And then what have I got here? So then I'm going to have, okay, I need a little bit of room because, yes, it's a bit of a nasty one, isn't it? Let me just shuffle that along a little bit. There we go. So that sec squared, on the denominator I've actually got sec to the 4. So that sec squared is cancelling out one of the sec squareds on the denominator. So I've just got 1 over sec squared. In other words, I've got a cos squared on the coming from all of this stuff. All of this stuff just gives me a cos squared. I've pulled that 1 minus e out, so that 1 has become a 1 minus e. And then I've got a 1 plus e tan squared phi. It's still not quite fitting for me. There we go. And I've still got that cos squared, right, that I haven't written down. So I've got to finally sneak in a cos squared phi. Okay, so I'm going to need a new page. But so I've done this substitution and it's all turned out quite nicely. Actually, that's a 1 minus e squared to the 3 over 2 out the front. And then if I times that cos squared in there, I've got 1 minus e cos squared phi plus 1 plus e sine squared phi d phi, and I think that's copied everything. Oh, I forgot to do the limits all the way. This is meant to be a definite integral, so these were t being 0 to infinity. So when t is 0, well, phi will be 0. When t is 1, I want tan. So when t is infinity, what phi is that? That's when phi is pi by 2. So those are my phi limits. Now I think I've got everything. Okay, now finally I think we can finish this off. You see, we've got this 1 minus e squared to the 3 over 2, which we were kind of expecting. So this is promising. What have I got here? I've got the 1's give me a cos squared plus sine squared. And then I've got this e cos squared phi minus sine squared phi d phi. And this is cos 2 phi. So now I can integrate. And the 1 gives me a phi, and then I get what an e over 2 sine 2 phi. And I just have to evaluate between 0 and pi by 2. But let me see, the sine 2 phi term when I evaluate gives me 0 in both cases. So it's only phi being evaluated, so that gives me a pi by 2, and I've already got a 2, so I finally end up with pi over 1 minus e squared to the 3 over 2. And amazingly, that's what I was expecting. So, okay, I bored you with a complicated calculation, which was kind of a bit gratuitous to go through, but it illustrates this substitution. So this is really what I wanted you to see, was this geometric picture of this strange substitution, t equals tan theta over 2. And I'm going to use that next time.